First, thank you, Bo, for agreeing to for filling in our speaker spot. I've been organizing the seminars together, and I was joking with him before that this is the way I actually get to know him a little bit more, is to ask him for the introduction. Because I hadn't realized, I knew that both of us started around the same time, so we've been here for 2.5 years. And both studied at the Wharton School at Penn, worked with Dylan Small. And so your focus is on observational studies, including their design and conduct and instrumental variables. I'm really very excited. I examine observational studies. It's something that's very different from what a lot of us do, right? So there's time for questions during the talk.
Yeah.
And yeah, so thank you.
Thanks very much for having me here. So today I will be talking about two sort of related products. They're both instrumental variables. I work with the IV quite a bit. So both talks will be centered around how to design, or in some sense, leverage strengths and instrumental variables. So I think it's pretty normal idea, so we'll find out. So I do have two parts of this talk. I may or may not be able to cover everything, but I will skip some slides if I think it's not necessary. So in the first part of the talk, I will describe the motivation for editing or development here. So I'll be concerned about how to strengthen a continuous instrumental level. So I'll first describe to a machine-based study design approach to IV analysis. I'll then describe how in some cases, people are talking a little bit after having strength and a continuous instrumental variable with the goal of deriving more informative inference. Of course, and now I'll have some my own critiques, and we will move from there and introduce some of the things that we pursue. And in the second part of the talk, we will switch to a binary instrumental variable. But if you have continuous instrumental variable, sort of at high level, it makes sense. In some sense, you can imagine strengthening the instrumental variable by making the IV levels fall apart. With the binary IV, it seems that we just take it as it is. And it turns out, I was interacting with the interior, it turns out that there are cases where we can have two versions of the same treatment assignment. So in some sense, the nature might create as a naturally strengthened binary IV. So I will then introduce an nested IV assumption, and I'll introduce some new estimands, some new principal strata for whom we refer to them as the switcher, and we would derive the switch average treatment effect. I would then talk about how this entire thing fit into the general concept of we want to generalize the effect estimate derived from instrumental variable. So first part, this is joint work with Min. She has contact PhD candidate at biostat, and it's Zoe, she has a PhD from the UPenn, currently a postdoc at Penn. So I'm going to describe a tale of two designs. So this is the modeling example, the data set that we've been looking at. In this paper, 2010 JASA paper, biology studied the effect of high level versus low level units for intensive care unit and NICU on infant mortality rate. So the treatment here is just 10 high level versus low level NICU. Outcome and 30-day mortality rate. Clearly, there is a lot of self-selection in what where mothers deliver their kids. And here, I need to mention, so all the children being studied here are preterm babies.
Just clarify, what's the difference, high level versus low level?
Oh,
The
yeah.
amount of care provided? Or...
Yeah, exactly. So they have technology advanced the ICUs in also called better hospital, quote unquote better hospitals. Versus the more community level hospitals. So this is the and then what the key here is people being studied here are mostly preterm babies. So they're delivered sort of, I'm not an expert, but they're delivered sort of not surprise in a lot of cases. So a lot of times the driver will drive them to the nearest possible hospital. And this creates the incentive to use this excess travel time. Essentially, they look at all the data, they look at the mother's zip code, vis-a-vis the nearest possible high-level NICU versus the nearest possible low-level NICU as an instrument for where the mother actually delivers. It turns out this is a fine instrument. The compliance rate is actually on the low side.
I was just wondering, it might be helpful to just define what you mean by an instrument.
Yeah,
It's
we'll
like
define
widely
this.
known, you're going to do that in
Yeah,
the
we'll do
part.
that.
You kind of have it
Yeah, exactly. So roughly, so it's like if you live closer to a high level NQ, you're more likely to be sent to high level NQ, roughly. This is an idea. And of course, one can, there will be IV outcome confounders that people actually are looking for later in the analysis. But typically, this will be the distance-based measurement is better, at least slightly better than the more self-selected high level versus low level individuals. Okay, so they did an IV analysis. So they adopted a study design. So they essentially the idea is they compare two similar mothers, similar age, sex, race, ethnicity, etc., but with very different access travel time. So here, access travel time is defined as time from their own zip code to the closest to nearest high level NQ minus time to the nearest low level NQ. So when I say a person has a large access travel time, this means this mother lives very far from a high level NQ, and so that this mother is discouraged from delivering at a high level NQ. Okay, so the treatment is high level NQ versus low level NQ. The idea is we're essentially this differential travel time, access travel time. So the key in that JASA paper is the major novelty. They consider two study designs, a more conventional one where they just utilize all data from Pennsylvania. They created the data is pretty rich. There are almost 200,000 preems over the last 15 years or something. So they create almost 100K pairs of two babies, but technically the mother and the babies. Okay. In the second design, they try to strengthen the instrument. They only pair two similar mothers whose IVs, whose access travel time are far apart. So instead of comparing two mothers who both live very close to the high level NQ, they compare mothers, one living very close to the high level NQ, one living very close to the low level NQ. Okay? But otherwise, they look similar. And in this way, they discarded half of the data, and they only create about 50K pairs after they strengthened this instrument work. So here's the intuition. Let's say you have four mothers that look exactly the same. They have different IV dose, 1 to 100, 101. You have different ways because it's a continuous IV. You have different ways to pair them. So I would argue, at least also argue that it's better to pair, for instance, 1 with 100 and pair 2 with 101 instead of pairing 1 with 2 and 100 with 101. The intuition is if you pair 1 with 2, very likely both mothers do not attend high level NQ. If you pair 100 versus 101, very likely both mothers would attend high level NQ. So there will be no compliance later when doing the analysis. But if you pair 1 with 100, 2 with 101, the compliance rate can be 100%. So I'll formalize these things. But here, this is the data I sort of recreate from their paper. It's not exactly the same, it's similar data. This is the way we try to recreate your analysis. So in this N0, this is essentially, we use pretty much all the data. So the near and far are summarizing essentially those mothers who live near, who live close, either far from a high level NQ or near a high level NQ. So as you can see, in a conventional design, this N0 here, the average difference in their access travel time is like 15 minutes. So turns out this 15 minutes will translate to less than 20% compliance rate. Not very high to the IV analysis, 20% compliance rate is not ideal. Other than that, the cohorts are pretty balanced. In the design M1, as you can see here, the access travel time now becomes 4 minutes versus almost more than half an hour. And they actually, by throwing away half of the data, the people who are lacking in the analysis after pairing actually have, on average, a lot larger differential distance, the difference in the differential distance. And the standardized mean difference increased from less than 1 to a little bit more than 2. Okay. One thing that I want to, okay, so of course, we have two designs. It's very natural to wonder what aspects actually change from one design to the other, right? So we try to summarize what changed from between their two designs. I think there are three things. So the first thing is the cohort on the investigation changed. This is pretty obvious. So in the first design, we have 180K people. In the second design, we have only half of that, 90K people. Okay. One thing that might draw attention is that the design 2 has much fewer black numbers. In fact, if you look at this, after they strengthened their instruments, only 4% of people are black in the strengthened design, compared to 15% as in the the entire state of Pennsylvania. Okay, and there's actually a very good reason for this, because Black mothers in Pennsylvania, they tend to live in urban areas. So we actually, this is a figure from their original paper. Yeah, I don't know, this is actually our recreation of their original paper, the figure in the original paper. As you can see, this is the effect distance. If you focus on those Black mothers, then almost overwhelmingly, they're actually pretty in the urban area, which means they actually a lot of them, they're very close to the large hospitals in Philadelphia, Pittsburgh, things like that. And when they try to strengthen the ID, it's very difficult to find two Black mothers who look similar, but one living very close to a high-level hospital, one living very far from a high-level hospital. Typically, they all live very close to a high-level hospital in their urban areas.
So in the matching, were you also matching by race then?
Yeah, that's a good question. So if you look at their balance table, the race is actually balanced in their near group and far group. They're both at 4%. So they would.
But is that by design, or was it, did you?
Oh, it's by-
Only based on, okay, so by
Oh,
design, you were also matching on all of these?
Yeah, they by design, they actually match on more cohorts. I can only show a subset of them because of the screen limit, but they actually match on 20, 25 cohorts.
Okay.
So race is one of the key things that actually match on. Okay, but nevertheless, the population got changed. Maybe for a good reason, but at least it's a change. The second thing that is changed is the compliance rate. So as I mentioned, two groups differ by 15 minutes on average in design 1.5 an hour in design 2, and the compliance rate as a result increased from roughly 20% all the way to 40%. 20% in the first design, 40% in their strengthened design. And which is not surprising, this is their initial goal in their design 2, right? They want to overcome the so-called weak IV problem by designing a stronger instrument. We've never seen this before, at least before this paper. And it makes some sense, I would say, but there are some caveats we could go. So there are some analytical results I used to derive. So essentially, if you look at the matched pair design, you pick the same test statistic. Let's say the treatment effect can be considered a constant treatment effect. The asymptotic relative efficiency comparing a weak IV versus a strong IV, actually the sample size equals essentially the ratio of the compliance rate squared. So if you double the compliance rate, you actually almost like creating 4 times more sample size. So in their case, okay, first of all, if the treatment effect is very constant, so that the distribution cohorts do not matter, if that's your assumption, then getting rid of half of the data to improve the compliance rate by 2 times is actually a gain. You will increase the power. Does that make sense? So this is a piece of a small analytical result, sort of justify what you're doing, of course, under a constant cycle. Okay, and the third thing that actually changed is the compiler subgroup. This is probably the most subtle thing. By changing who is matched to whom, the definition of the compiler subgroup actually changed between these two designs. This is a little bit subtle because the compliance category with a continuous instrument is defined with respect to continuous diagnosis. I will formalize this later. So intuition is, for instance, in a pair, a mother with 5 minutes is paired to a mother with 30 minutes. So what is compiler with respect to this ID dose 530? A compiler with respect to 530 as a mother who would attend a low level EQ when IV equals 30 and a high level EQ when IV equals 5. Okay, so the compiler here is defined with respect to ID dose. This is important because in the original paper, they studied an Estimands, which is referred to as the effect ratio. So it's essentially the sample average treatment effect among the compiler. It's if you do ID analysis, it's essentially the word estimate. They are interested in the compiler average effect. Okay. The tricky thing is, of course, when latent compiler change, their estimates change. So that what they are actually estimating is different between two designs. Of course, this difference will go away if you assume there's a constant treatment effect. That doesn't matter. Everyone has the same data, which is fine. But if you believe some heterogeneity, then the estimates will change between these two designs. Okay. So 3 things changed. Actually, the ID analysis is mostly suffer from people's critiques because it is slightly, at least this the word estimates, this complied average effect is very different from a traditional statistical analysis, because Zhe Chen, he's a famous economist, he said like IV analysis is the opposite of a standard statistical practice, in which a parameter of interest is first defined, followed by estimators that delivers that parameter or estimate. Instead, with an IV analysis, we have control with the light, meaning the IV, but we choose to let it fall where it may, and then proclaim whatever we found is what we are looking for all along. So it's actually saying that, you know, the comparison of that, because we don't pre-specify who the compliers are, you just estimate the so-called complier fact and just say, okay, the complier fact is this, even though it's not necessarily generalized to any target population that they're interested in. Of course, this is pretty controversial. A lot of people like hiding about this. But we were not trying to discuss what's correct. So our goal is try to see if it's possible to clearly state what is desired to be sought after, and then adjust the brightness of the light to the extent possible to illuminate the object that we are sort of seeking after. Okay, so what is the object we are actually trying to illuminate? So I would argue it's the sample average effect of the treatment received on the outcome of the entire cohort. Okay, so we're not most interested in ITT, in intention to treat effect, especially in this type of observational study. The idea is something that we create in order to deliver the sample average effect or to illuminate some kind of effect. Different people can find different ideas. So the effect of IV on the outcome, that is the intention to treat effect, is typically not of interest. And also here, we would move one step further. We don't even want to estimate the local or the compliant average effect. We want to estimate or to some extent derive some information for the entire sample average effect, the proportional. What happens if these 90K people or 180K people all sent to a high level EQ versus all sent to a low level EQ? What would be the difference in their survival outcome?
So, okay, just to clarify a little bit, so the IV, that's something that's related to the treatment, but not the outcome.
Yeah, yes, its effect on the outcome will be mediated through the treatment.
And it's thought of as a natural randomizer.
Yeah.
Which is where the compliance comes from.
Exactly.
So, and that's why you're adjusting for all of these other, you're matching on all of these other things to remove that relationship to.
Yeah, the goal of matching on those background cohorts is to make sure that IV is more like a randomizer.
Yep.
And because IV, living close, we can argue people living in different places because of other things. I can argue healthy people who tend to live in urban areas. So they try to match on cohorts, so this IV is more like a randomized.
Natural randomizer, yeah. So the question I have is, if you're strengthening the IV, you're increasing the brightness, but then you have to throw out, like, how does that affect the generalizability? Is that what you're gonna get to?
Exactly.
Okay.
That's the key, exactly. But here, so for one thing, we don't have to throw away anything. You can keep the entire cohort, just change with match to full. Even by that, you can increase the. But of course, not as much as if you throw away some data, but you can still materially improve the capacity. The example is 1 to 100, 101 example I gave. I don't have to throw away anyone. I can just change with match to full. I can just match, when I match people, I just say match all those with titles. I never want to match two people with a similar encouragement or iron dose. Okay, that's what I mean by change the brightness. Okay, so but eventually the estimate here is the sample average effect, the proportional effect. Okay, not the complier effect, not ITT. It's not identifiable, we're going to bound it, but still. The advantage of this estimate is that it's defined irrespective of the ID or the matching design. There's always a well-defined estimate. What happens if I send 180K people to high-level EQ versus 180K people to low-level EQ? IV is literally just an instrument. It's a tool for us to learn a little bit of information. But this estimate, the sample average effect, is not defined with respect to IV. It also is not defined with respect to the vegetable. Design is irrelevant. IV is not irrelevant. but the choice of ID and the choice of design could shed different level of insight on this estimate. So, but again, these are a little bit, high level. I'll again make it a little more concrete. So, even before that, we actually solved a small problem along the way. So that's the first thing that is different, even without this compiler thing, is the study population is slightly different. So we want to, we sort of modify the matching algorithm, and we develop a template matching program that is designed to at least when it's with some people it's fine, but at least make it so that who is remained in the sample looks similar to the entire population. And I'll skip the algorithm, I'll just show you the result. M0 and M1 are what we just described. We call M0 is everyone, M1 throwing half of the data. They don't care who they throw away, essentially. They just throw away people who they cannot find a match with a very different ID, essentially. But in this match too, we do care about who we throw away. We throw away only about 10% of the data, we retain most of the data. As you can see, the access to travel time, the instrument is now like 2 versus 27. It's not as good as 4 versus 35. I would argue it's close, it's comparable, and we do not really throw away people regardless of who they are. As you can see, we also retain the 60% black matter portion in the sample. So I only trim a little bit. We don't even have to trim, actually. You don't have to trim. You can still, just by changing who is actually who, you can materially improve the chemistry. The SMD increased from 0.9 to more than double, to 1.88. We largely keep the population. So later, we are going to focus on this match too. So I'm interested in the sample average treatment effect of high level versus low level NICU of these about 165,000 mothers in Pennsylvania during like a 10 or 15 year period.
And is your matching, it's a 1-1 match?
Oh, it's a pair match, yes.
Yeah, okay.
Yeah. Although, yeah, I wrote that paper maybe last year, we also do a complete subclassification. It does not need to be a pair match. It can be a bunch of match classes, match sets with different sizes. It has two randomization.
So what is the match to design?
Say that again, please.
What is the match to design? What is it?
What is the
Match one here, you are matching and one is near, one is far away.
right? Exactly. Just
What's
pair.
the match to?
The similar thing. It's just a low ID versus a high ID, but the ID is continuous, so it's not a binary thing, right? So we can change who is paired.
So it's almost like, so you have like a function for the match, so you're matching also on all these 20 plus covariates.
Mhm.
So you can have a distance, so for the covariates, you want them to be near.
Exactly.
And for the travel time, you want to be.
As reference point, yes, exactly. We want people who are similar in covariates, but they are different in their weighted position, in their differential travel time. At the same time, there are tuning parameters, you can throw in some people, but you don't have to. Here I throw 10% because at this small cost, we can improve the compliance rate by like almost 2 times, which I think is a very good, it's a favorable trade-off for us. Okay, just for the sake of time, we just sort of move on. So here is the key thing we need to define what is the Estimands sum and outcomes. So here the Z tilde is this continuous instrument. Okay, so once I have OBS, it's a reserved, but the Z tilde is just the abstract random variable. Yeah, input will be conditioning on them, but think about it as a random variable. It's a continuous instrumental variable. It's D of Z tilde, D is the binary thing, high level versus low level output. Okay, it's a binary potential outcome. So it is a for this person, IJ. So where this mother would deliver if this mother lives 5 minutes, or 10 minutes, or 15 minutes, or 20 minutes. This is the philosophical thing. This is the abstract thing. Of course, we only observe one realization. In practice, this mother lives between 22 minutes, and we observe a realization E22, which is the 1-0, depending on where that mother delivers. Okay, so here with each pair, we would define, it's just a notation, the minimum versus the maximum of the 2 doses. For instance, if we pair 5 with 30, then 5 is the minimum, 30 is the maximum. Okay, so here the first potential outcome definition is this DT and DC. So DT here is your potential delivery hospital if you live Like in that example, 30 minutes away from the hospital. And DC is where you would deliver if you live only 5 minutes away with each hospital. This is our DDC, and you can just there are in IV analysis we have full compliance category. You are either complier, that's where the DDC is 10, always taker 11. If that's no, doesn't matter 5 or 30 minutes. I always deliver in the high level hospital. Never taker 00, doesn't matter 5 or 30 minutes. I always deliver at a low level hospital. At the fire is 01. We will make the so-called non-implicit assumption. We assume no defiers. So there are no people who would deliberately act that is contrary to their incentive. So, but we would have both taker and non-taker and compounds. So the key definition too here is what we refer to as RT and RC. So RT is this mother's child's potential outcome if this mother lives, let's say, 5 minutes away versus 30 minutes away. Okay, RT is 30 minutes away, RC is 5 minutes away. Okay, so this is the potential outcome on the encouragement. This is the difference between them is some version of the intention to treat. This is not a purportable treatment effect. This is defined. This potential outcome, R outcome is defined with respect to the IV instruments. So this is only like some kind of a potential outcome on the encouragement. To differentiate, we also define this RD1 versus RD0. So RD equal to 0 is what happens to this mom and her child. If I send a mom to the low-level hospital, versus what happens if I dictate, I just send you to the high-level hospital. Okay, so the potential outcome under the potential outcome under so-called protocol treatment. So the real treatment I'm interested in. So usually the difference between these two things that does not necessarily equal the difference between RT and RC here. Mostly because the compliance rate is not 1. If the compliance rate is 100%, then these two things are the same. Otherwise, they're not the same. The first one is the so-called protocol effect. The second one is the intention to treat effect. Of course, it's a unit level intention to treat to most of us. Okay. So in the original paper, they studied the word estimate, the factor ratio. So essentially the lambda has the following interpretation. In their design, for every 100 mothers who are encouraged by where they live to deliver at a high level hospital, how many deaths we can avoid? I think the estimate is approximately 0.9 or 1. So for 100 mothers who are encouraged to deliver at high level hospital by where they live, then approximately the outcome differ by 1. So this is their interpretation of this compliant average treatment effect. Well, of course, a natural question is who are those 100 mothers who are encouraged by this particular IV to deliver at a high level hospital? This is not clear. But of course, they also acknowledge that. But anyway, this is the in IV analysis, this is the usual word estimate session. Okay, well, what we are interested in, I would say ultimately people are interested in this kappa here. This is the sample average treatment of D on Y. So everyone sent to high level hospital versus low level hospital, what's the average difference in their mortality rate? Okay, so the most important thing is here, the Estimands does not depend on IV, right? The entire thing does not even have Z in this definition. And also it does not depend on who is matched to, which is this is why this is a good estimate to pursue. Okay, the key thing is usually without very strong assumptions, the kappa is not identified in IV analysis unless the compliance rate is 100%. Unless you make some other assumptions. For instance, some assumption may say the compiler effect is the same as the effect among the compliers, which is sort of like a trivial assumption. You can use that to generalize. But here we persist on something slightly different. It's also a pretty usual route. So when we cannot fully identify it, we just partially identify or we just bound the kappa. So here I'm just describing assumption-free bound. So all it needs is that we assume the treatment effect is bounded because the outcome is bounded. In the case of mortality, it's always bounded between 0 and 1. It's a trivial bound, but of course you can say, I believe the treatment effect is somehow bounded between this and that. Okay, let's say K0, K1 is a bound on the treatment effect for everyone. So we can show pretty easily that the target, the kappa, the standard average effect, is lower bounded by this LB expression here, upper bounded by this UB expression here. The key thing I would like to stress is if you look at the difference between LB and UB, the length of the bound the first term would cancel out. So what is left is essentially the compliance rate. So this is why you can do the same thing. You have the same data, but you would derive different bonds just by changing who is paired to whom. Because the length of the bonds actually only would depend on the compliance rate. If I change my pairing, improve my compliance rate, I could shorten this partial identification bonds. Okay, so again, I just try to stress. So using the same data and therefore the same sample average treatment effect to be bounded, same estimate, something that we are trying to pursue. Strengthening I will reduce to a narrower bound at no cost. We're not changing the population, not changing that.
Oh, maybe I missed a part. So I think your last slide, we also talked about like it does not change with who is matched to who. But here, for example, your estimate and also the balance are kind of related to summation of I and J. So it's kind of related to how you match individuals, right?
Okay, so here, this kappa, right? This
Right.
kappa IJ runs over everyone. So in that population, 200K people, IJ just runs over 200K people. So this summation just gives you the sample average effect for that 200 people.
Maybe I think it's like J, you have 1 and 2, right?
Yes.
So if it's for, so, okay, for the like 20K individuals or 200K individuals will be the I here.
No.
It will be-
I times J is 200K. So 200K people, we form 100K pairs of 2. Right, we start with 200 people, we form 100,000 pairs, each having 2 folks. So the I runs from 1 to 100K, J is either 1 to 2. So we sum them up, it's just eventually the entire cohort, 200 people.
Right, and then my question is like, why does it not depend on who is matched to whom? Because it's entirely this M0 matching you start with, right?
Right, it does not depend on who is matched to whom because you can change different ways that you construct those 100K pairs. Okay, but eventually it's the sample average effect for each one. This is the target estimate.
It was like the sample average across all those pairs, right?
I mean, everyone. So for instance, back to that example, 1 to 4 persons, 1 to 100, 1. I'm interested in the sample average effect for 4 of them. It doesn't matter if you pair 1 to 2, the first 2 person, the third and fourth person, or you pair the first and third, the second and fourth. Eventually, I'm just interested in whether you effect if you send all 4 of them to the higher level hospital versus what happens if you send all 4 of them to the lower level hospital.
Oh, I see. Yeah, thank you, that's really useful. So like,
Exactly. So that's really tricky. So this is also why here I do a match pair. But it doesn't matter if you have a match stats design. I and J can run over I to Ni, number of units with each set. Eventually, that summation is over every single one in the sample before matching. Doesn't matter.
But this is just like potential outcome notation?
It's not that this is potential outcome. Of course, this is estimate. I haven't described how actually estimated. But of course, in practice, we only observe one generalization, so we need to infer this kappa. And the way we infer this kappa is we first bound it. We just acknowledge it's not readily identifiable unless you have very strong assumptions. But this bound is true. This bound is always hold. As long as the outcome is bounded or the treatment effect is bounded, this bound will always hold. And this bound LBMU actually depends on who is matched. But it doesn't matter. So the interesting thing is, I think your estimate is always fixed. You have different design, we construct different LBU, different bounds. But it doesn't matter where those bounds are, they always contain the truth. But some bounds are better than others, because some bounds are narrower than others. This is why we never change the data, we change the design, how we pair data. And the goal is to do a more informative inference, to make your LBMU be narrower. It doesn't matter if the one is narrow. Your design might be very wide, my design might be very narrow, my bounds, but we all cover the truth. We all cover the same truth, the same parameter that we are trying to estimate. That's sort of the high level idea. And of course, you see the LB here involves RT, RC, TDC. We only observe one, not both potential outcome, so we need to make inference. And essentially we can do inference, we can test LB equal to little L, for instance. But okay, here first inference is just based on randomization. But still, within each pair, you have randomized because After pairing these two mothers, 5 versus 30 minutes, the chance that first mother lived 5 minutes versus the second mother 30 minutes is the same as 30 versus 5. So within each pair of randomization, this is our reason basis. This is why I can make inference. Otherwise, you would never make inference because you never observe simultaneously RTRC or DTDC.
Or the original study here is the randomized trial, or here is the observational study?
It is observational, but they assume this instrument is randomized after pairing on this.
So then you imagine that, so then for match two, then you are using all the possible pairs. If that's the case, you don't need to, you see, then to drop any of the data. But you still, you see, the kind of dropped about 10%.
I don't have to drop the data, but the thing is here, I drop 10%. My remaining people, the distribution coverts look like the entire cohort. And also I do gain a little bit more in my compliance rate. So I think it's a good, it's a favorable trade-off. But you don't have to, if you don't drop anyone, it's also fine. You can still, by changing the pairing, you can improve the compliance rate from 20% to maybe 33%. But here we can improve it from 20% to maybe 38%. I think it's a, and drop, yeah, you don't have to drop it. That's the good point. So the thing is, we can make inference on the randomization of this instrument. The treatment is not randomized, but the idea is randomized. So we can derive a valid inference essentially for both the lower bound and upper bound, and do a bound for own, you can construct a valid inference. It's technical confidence interval. It's always covered the ground truth with at least 95% confidence, or probability. And of course, in the paper, there are standard machinery. You can improve the biostat-seminar using covariates. I never use covariates in this expression. You can. The covariates will go into the biostat-seminar. It actually will make your inference slightly more efficient if the covariates predicts the outcome difference. And also, we mentioned in your paper, and actually another major thing we try to do is this randomization assumption actually has testable implications, and it can be rejected. So what's the randomization probability? So here, essentially, in each pair, the probability that first person received the 5 minutes and the second person 30 minutes, versus the first person 30 minutes, the second person 5 minutes. This is the match pair. Just think of a match pair experiment, right? This probability need not be a half. Okay. So again, the other thing we do is we test the null hypothesis, the same null hypothesis, but under a bias randomization scheme, where we allow the maximum possible bias with each pair to depend on ID dose difference. And this has a very clear motivation. If by chance you pair two persons with the same ID, it can happen. Then this pi by definition has to be half. What's the probability of the first person in 5 minutes, the second person also 5 minutes? It's the same as you swap 5 by 5. So this motivates this dose dependent, ID dose dependent bias randomization scheme. Anyway, long and short is essentially we also can derive a lot of inference under this bias randomization model. And it's a little bit novel because typically, this is reminiscent of the Rosenbaum bounds, but they typically operate under a binary treatment or binary thing. We sort of generalize it to allow the extent of maximal deviation from half randomization to be dependent on the ID dose, which I think is a reasonable thing. Okay, so here is what we can analyze, how we analyze the data. So we analyze the outcome mortality and the composite outcome mortality also plus the length of stay. So here we do make it. So if you maybe remember, this K1 and K0 is the bound on the treatment effect. So we do assume here into when we make this plot, we do assume receiving treatment for each person, receiving treatment at a high level hospital does not hurt you. You cannot survive at low level hospital, somehow die in a high level hospital for the same person. Of course, it may not hold 100% of the time, but I think it's a pretty reasonable assumption. Receiving treatment, the same person on the same condition at a high level hospital cannot hurt you. Okay? But how much gain you get is this K1. This K1 is trying to, this is sort of like the bounds. So essentially, for instance, if you believe the maximum treatment effect among the entire population is, let's say, bounded between 0 and 2%, then this lower in confidence, lower in upper bound is telling you what is the sample average treatment effect we actually observe for this data. And the good thing is, so here, the solid line here corresponds to the bias randomization. So this confidence interval from this yellow solid line to this purple solid line, it actually takes into account different levels of uncertainty. It takes into account the fact that the treatment effect is not identified. It also takes into account that this IV is not perfect. We actually do a bias randomization when we construct response. And of course, it also takes into account the sampling variability because it's a random sample. So essentially in the paper we report, but let's say if you believe, for instance, the maximum effect is at most 2% for any person, then the treatment effect in high level versus low level hospital is given by like slightly lower than 0.5%, probably 0.3% to roughly 2% for this the data that we actually observed from Florida. Okay, so that's just an illustration. For the sake of time, I need to move on. So yeah, the paper is archived a while ago. So yeah, we submitted to JASA and we very recently submitted a revision there. So everything I just described was based on that biology paper where they describe how they can strengthen continuous instrumental variable. A more typical example is, for instance, in clinical trials, we have randomized treatment assignment. It's also like an IV, right? Because people do not necessarily take the treatment. So, but in those cases, the instrumental variable is binary. So what we are very interested in is it possible to actually strengthen a binary instrumental? Typically, it is not, but in some cases, it turns out it seems that nature might create some opportunities. So again, this is joint work with Ray, Oliver, and Yingqi here. Again, I will go back to Zhe critique. Again, remember, we can always non-parametrically identify the complier average effect. I personally like it, I think it's more elegant. But it's never clear if the effect among compliers actually generalized to a large population or the entire population. There are different ways to tackle this. I think the most usual way is just to propose suitable identification assumptions that help link the so-called the local or complier average effect to the average treatment effect or average treatment effect on the treated ADD. So Jamie, Eric, Stang, and they have all kinds of stored here. I think they all propose different types of identification assumption that essentially tells us under what assumptions when essentially the effect you can non-parametric identify under this complier group actually can generalize to the entire population. But the estimate is typically the same. You ask me the same thing. They're just endowed it with a different explanation, interpretation. So we try to do is try to go beyond a little bit of, at least go a little bit beyond this level. So here is I think a pretty intuitive example. So let's consider we run a multi-site, multi-center RPT. We run this RPT in two very similar clinical sites. Let's say Seattle and Portland. Okay. So the compliance rate in Seattle is 50%. The compliance rate in Portland is 100%. Suppose we ask an IPT, which is true. Okay, we always have intention to treat the fact that in Seattle, risk difference scale 22%. Okay, if we genuinely believe that the protocol effect is homogeneous, more or less homogeneous, and generalizable, then I would expect that intention to treat effect in Portland would be roughly 0.4%. Right? I have we double the compliance rate, I should roughly see a doubling of my intention to treat effect. Otherwise, there's no point of improving compliance. Right? The goal of improving compliance to a large extent is to improve the ITT. Because if we believe the treatment actually matters, then we would expect to see the ITT in Portland to be roughly 0.4%. However, if instead we observe the effect of 0.22% in Portland, okay, then I think I would argue that this is evidence against generalizability. Okay, so if I offer my intuition, the intuition would be essentially whoever under stronger incentive to participate in the trial and be adherent to the treatment has a negligible effect on these additional compliers. This is why, for instance, in Portland, I only see a very slight increase in my intention to treat effect. Okay, so we again, the goal of statistics, we just try to make this intuition a little more rigorous. We are going to define and focus on what we call the switcher population. Okay. And this is another example that sort of got us to start thinking about this. So in PLCO, we do have it's a clinical trial with non-compliance. So there are 3 centers that initially adopted a dual consent process, but later switched to a single consent process, mostly because of compliance rate. So in this paper, Marcus Dahl, they found that a single versus dual consent actually resulted in a much higher compliance rate, even after adjusting for a very rich set of baseline cohorts. I think the odds differ by more than 2-fold. So we are going to try to formalize it. So the thing is, so the basic economic stats, if the encouragement is strengthened, more people would comply. Okay. So here we are going to define 2 versions of a binary ID. Okay, we always have a binary ID. If you go to Seattle, it's either randomized to treatment or control. If you go to Portland, it's randomized to treatment or control. But we're going to make a distinction between the version that's 1, the version that's 0. Okay, so for instance, here we consider 2 versions of binary ID. 0A, 1A corresponding to assignment to treatment control. For instance, in Seattle, 0B, 1B would denote randomization to treatment or control. That's important. And then another example, 0A, 1A would denote randomization to treatment or control. For instance, during the dual consent phase, had a person enrolled in dual consent phase. Now, let's imagine this person, instead of before 1997, the person enrolled in the trial in 1998, and then the trial has already switched to a single consent process. Then 0B, 1B would be the randomization to treatment or control, had a person enrolled and randomized during the single consent phase. Okay? So by introducing these 2 versions of binary ID, we would immediately, essentially, we'll have more principal strategy. So there will be people, hypothetically, just they sort of live in your mind. These people are like always complier. So if the person enrolled in Seattle, the person would be a complier. If the person in a counterfactual in a parallel universe enrolled in a clinical site in Portland, the person would still be a complier. I would call this person always complier. Okay? And of course, there are also people who would be a never taker or always taker if the person enrolled in Seattle, but become a complier. The person would then be a complier had the person enrolled in Portland. Okay, so we would call these people switcher. So I think this is sort of a key thing. We need to establish that because we can think of a person, we can think of so-called potential, we can define potential outcome under randomization to treatment or randomization to control. We can also define potential outcome under randomization to treatment in Seattle versus being randomized to treatment in Portland. The key assumption that enables identification is, which I think is probably the least, it's a pretty reasonable assumption, that we call the synaptic assumption. So we say, if a participant is a complier under this weaker version of instrument, right, then the person will remain a complier on the stronger version of the type. So I'll give you an example. So the most trivial example is here. Let's say randomizing to placebo always mean the same thing in Portland or Seattle. Give you some pills, placebo, do whatever you want. Let's say so 0A equals 0B. Okay. This is not essential. This is just a simple example. Okay, 0A equals 0B. 1A meaning encouragement to take intervention. Let's say in Seattle, which may entail I give you a follow-up course. We typically do some education programs. Sometimes we give compensation. Okay, so this is what happens in Seattle. 1B is again, it's a strengthened version of encourage people to take the intervention. I'll give you more course. In the most straightforward way, I'll give you more compensation. If you come back to me with a bottle that has no pills, I give you $100. I give you an Amazon gift card. So people have more incentive to actually adhere to the treatment. So for instance, in this case, the assumption essentially is that if the person is a complier on the 0A, 1A, then the person remains a complier under the stronger version of encouragement, 0B, 1B. But of course, this is, in general, we don't assume 0A equals 0B, but this is just a simple example. And the most important thing is, you see, the assumption only stands if you are a good, quote unquote, good person and being adherent to my treatment assignment. If you are a good complier, then you remain a good complier in a stronger IB setting. but we do not need to make any assumption on any other folks. For the other folks, if you are a never taker and remain a never taker, fine. If you are a never taker, become an always taker, fine. Doesn't matter. For the other principal strategy, you can whatever. But a good compiler on the weak high, you need to remain a good compiler on the strong high. This is a philosophical thing. I don't think you can. At least I don't see any way to test it. But I think it's more or less a reasonable assumption. Okay, just for the sake of time, I would essentially say then we actually have these principal strata. We have always never takers. You know, when you do whatever, you can give them however money you want as incentive, compensation, doesn't matter. The people is a never taker, no matter where they go. Okay, they're always never taker, they're a switcher. This is something that I'm interested in. People who are not compliant on the weaker version of the instrument, they become a compiler, who would become a compiler on the stronger version of the instrument. And people who change from always taker to never taker, who change from never taker to always taker, people who are so-called always taker. People, person likes taking has a screen. The person remains that way, no matter where the person involved is possible. So among all these things, eventually I am interested in the so-called the switcher, the conditional switcher average effect. We can, among all those different populations, there are two populations whose effect can be non-parametrically identified. So they are the so-called always compiler. So this is the compiler no matter. We can identify the effect among always compiler. We also can identify the effect among switcher. People who will not compile but become compiler. Okay, so this is actually still this plot from Yingqi. So essentially, you think of the entire population. So we have a subgroup who are compiler to this weaker intervention on the Z1, who adhere to the compiling intervention on this weak IV Z1. This population, the middle, they would compile to the intervention on the Z2 because Z2 is stronger version, strong encouragement. And if you just superimpose them, and this figure is just a simple illustration. It does not need to be like this, but the entire population could be considered always compilers, switchers, and always never takers. So people are, and the switcher here is essentially the difference between these two squares. And I'm interested in the effect among these people. Okay, so I would just say we can identify the effect among the switcher population, and a very natural question is, people ask, you don't know who the compilers are. Why bother estimating the compiler effect? There's a counter argument. In fact, we don't know for each person if the person is compiler. However, we actually can estimate the covariant distribution among the compilers. So we don't know for each person if you are compiler because I never observe your treatment status under the other treatment assignment. But as for the population, we actually can quantify what the compiler roughly look like. We can do the same thing for our switchers. So here is what happens to that PLCO trial. What are those switchers? So essentially, it's an integrated data analysis of pre and post 1997 data, dual stage, dual consent stage, single consent stage. Roughly the compliance increased from 50% to 90% after they changed this protocol, the way that they consent people. So here is how summary statistics, table 1 of all the always compliers and then the switchers. I think it's actually pretty interesting. When we estimated it, it turns out those switchers are actually pretty different from the population in that they are more likely to be female, and more likely to be white, and they're more likely to have a smaller than 25 BMI. So this is essentially describing that latent switcher population estimated of course under the natural assumption and using our proposed estimate. I'll just say that the switcher we derived essentially EIF efficient influence function based estimator. So this is some simulation study. A rule of thumb is if the sample size times the proportion of switch is larger than 500, the inference is pretty accurate. Small bias, nominal coverage, asymptotic normality. And I will just also just show you with this PLCO data. So the risk difference was estimated to be like roughly 1%, but not significant for switchers, and the negative 1% marginally significant for always compliers using the CIF based estimator. Okay, so the key is the switchers. There is no treatment effect. So the treatment, you are more familiar with the treatment is cancer screening, the real cancer screening. Outcome is 15-year colorectal cancer rate. So ideally, we would want to see the switcher I don't know what we really want to see, but hopefully the treatment actually matters for switcher population as well. But it seems, when estimating about for switchers, it's pretty wide confidence interval, and also there's not even a hint of evidence that there's a treatment effect. Back to the intuition, I think that's a reasonable thing from the data, because in the pre-1997 data, the intention to treat effect is minus 0.26 per 100 procedures. The compliance rate is roughly 50%. The post-1997 data, the compliance rate is about 80%, but the ITT actually does not increase as one would hope. I think the ITT is actually like 0.14. So put together, they say during later period, we have much higher compliance rate, but the intention to treat it actually somewhat dilutes. So put together, if you go back to my initial intuition, it's essentially a net population for whom that become compliant after the protocol change, there is negligible effect on these people. So again, who are those switchers? We say they tend to be female, white, BMI, small BMI. I did a little Google search. It seems reasonable. This is the population have a very low colorectal cancer rate. So then I think it's probably reasonable because they have so low cancer rate to start colorectal cancer rate to start with. Cancer screening does not really have a material effect on lowering their already near zero colorectal cancer rate.
I mean, the other thing is there was crossover and uptake in there was contamination, I think. But I'm just gonna.
I think that's fine. So that's actually my last question. So there's a link to the paper. I think we'll also distribute some minutes to just. Okay, so that's it. Let me know if you have any questions. I mean, we have time for
Okay,
questions.
first, thank you. Really good.
Yeah, I actually have a question. Okay, so I wonder, so consider a different trial which have like two type of, like randomized to 3 arms, with 2 different type of encouragement. So for example, when you talk about like this, follow-up calls and compensation versus more calls, more compensation. I just wonder, just in terms of, one difference I can see from that trial design to what you have is basically there's no randomization for this 2 type of encouragement involved here.
Yeah, there is no randomization. So yeah, there's no randomization in terms of ideally, I would randomize people to enroll in Seattle versus Portland, but at this step, this is not randomized. That's why I would actually control for them cover.
So like that's kind of your mean distribution.
Yeah, exactly.
Yeah, I just wonder just in terms of methodology, how different it is from this kind of, if I have another trial with this IV, it's just 3 levels, and then like, so what's the difference in terms of?
Yeah, I think if the IV is 3 level, it's sort of then go back to that 0. So the control arm is the same. You can compare essentially. It's almost like this. Right?
Yeah.
You can have 0, 1, 2. I think it is sort of more like an ordinal IV. But you can, I think the similar idea sort of applies. You can actually estimate if you have a 3-arm trial, 1 or 2 intervention, 1 intervention, the second intervention is stronger than the first intervention, then actually you can estimate. You can again, intuition will be compared ITT of intervention A versus control, intervention B versus control. And then you can do the same thing here. You can actually estimate what is the switcher effect, what is the populations, the treatment effect among the switcher population. So, and what I didn't describe here is after you obtain the switcher effect, you actually compare it to the always compliant effect. And this gives you a way to actually test if the treatment effect is actually generalizable. I didn't describe it in the thing paper because eventually what we have here is we can identify this effect. We can identify the effect among these people. These people I can compare conditions on covers. So that this gives you a way to, instead of just arguing that IV that's generalized, there's a testable way to say, does the IV that's generalized? Okay, cool. Thank you very much.
Thank you.